Okay, testing. Hello, hello, testing. Okay. Lucy, are you opening? Okay, great, great. Join. Okay, you're getting on the laptop, I guess. Okay, great. It's coming up. Your screen has come up. Yeah, make it a little big. 175. Yeah, one more. Click one more time. Okay, great. Now you can go ahead and start. Yeah, I can hear you. There is some echo, so make sure the both of your mics are not on. Switch off the phone mic. Yeah, now it's perfect.
primitive CP and IP-based distributed applications was demonstrated at supercomputing in 1991. On that occasion, the remote visualization of large and complex scientific data sets
Uh,
in a high
Lucy, is there some, I don't know where's the background noise coming from? Is there some music or echo? I do not know what is happening. Hello?
It's fine now.
Yeah, now it's perfect. Thank you so much.
So, on that occasion, the remote visualization of large and complex scientific data sets, a high-resolution magnetic resonance image or MRI scan of the human brain was set up between the Peterborough Supercomputing Center, that is BSC, and Albuquerque, QQ. Am I correct, sir?
Yeah, no problem. You can go ahead.
New Mexico, the location of the conference. Then a further step was made by DICER project, which made available as remote data sources, high data rate, and online instrument systems. Still on high, the project leveraged the wide area large data object or Hadoop system, which was used to provide the following capabilities. The first was automatic generation of metadata. Second was automatic cataloging of data and metadata while processing the data in real time. Third, facilitation of cooperative research by providing local and remote users access to data and mechanisms to incorporate data into databases and other documents. The first data-intensive environment is reported to be the MAGIC project, a DARPA-funded collaboration working on distributed applications in large-scale, high-speed networks. Its context, the distributed parallel storage system was developed and later used to support TeraVision, a Tetrane visualization application that lets users explore and navigate a three-dimensional real landscape. Another important milestone was set with the Clipper project, a collaborative effort of several
Hello? Oh, hello. Is your screen freezed, Lucy?
Sir, what did you say?
Your screen is freezed, I guess. Yeah. Can you go ahead and read? We can't hear you.
Yeah, you can go ahead.
Yeah, no problem. Please go ahead.
So, data grids mostly provide storage and dataset management facilities as support for scientific experiments that produce huge volume of data. Example, huge amount of data are produced by scientific instruments like telescopes, particles, accelerators, etc. visual observatories, which are collections of interoperating data archives and software tools that uses the internet to form a scientific research environment in which astronomical research programs can be conducted. This allows scientists to discover, assess, analyze, and combine lab data from heterogeneous data collections. Okay, so that's all. More questions? So should I go ahead with data clouds and big data?
Yes, Lucy. Please go ahead.
Okay. Let me move over to data clouds and big data. Big data term characterizes the nature of data-intensive computations. Today, identifies data sets that grow so large that they become complex to work with using on-hand database management tools. Massive amounts of data are being produced, mined, and crunched by companies that provide internet services such as searching, online advertising, and social media. Block analysis is an example of a data-intensive operation that is commonly performed in this context. Companies such as Google have a massive amount of data in the form of logs that are daily processed using their distributed infrastructure. The result, Google settled upon an analytic infrastructure which differs from the grid-based infrastructure used by the scientific community. Relational databases and desktop statistics or visualization packages become ineffective for that amount of information, instead requiring massively parallel software running on tens, hundreds, or even thousands of servers. Big data problems are found in non-scientific applications such as internet texts and documents, vaccine, call detail records, military surveillances, medical records, photography archives, video archives, and large-scale com- e-commerce. Distributed databases are a collection of data stored at different sides of the computing network. Each site might expose a degree. This is repeated, sir. We have read this before. Okay, now it's homework lessons. Huh?
Yeah, that's fine, Lucy. Thanks for reading through. Now you can mute yourself and unshare the screen. Okay. Okay. Hold on. So that was a lot of slides to cover. Okay. Can somebody confirm if my screen is visible and if my voice is clear? Okay, great. Thank you for confirming that. And so let's yep, okay. Okay, so the topic that we yesterday we started with data intensive computing, right? So we explained what data intensive computing is all about. Data, and it is not about less data, right? We are talking about a very huge size of data, something that starts with 1 terabyte to the least. So data can be collected at 1 terabyte per second, right? There is so much of data generated at every given time that you know you need to have a proper solution to handle data intensive computing. So we studied about the 5 V's of a big data yesterday. No, sorry, the 7 V's, and we also looked at the 8 elements that are involved in any data intensive computing. So today we started with the evolution, right? Where at some point there was a, so in earlier days we were building websites, right? So we had a kind of a three-tier architecture, something like a database is there, and then there is a web server which is hosting your website, and there is a browser, right? So this was a kind of a three-tier architecture, and this is also in your unit 4 this is kind of referred to as layered architecture also, the three-tier architecture. And I've seen questions on layered architecture in your university exams. So they kind of ask you, please explain the layered architecture. So you need to be aware that when they speak about layered architectures, they're talking about a multi-tier architecture, something like a three-tier client server architecture. So in this kind of architecture, the databases that was used was RDBMS, and RDBMS had limitations, right? Yesterday we spoke about that you cannot change the database without changing the design. So you need to stop the database, change the design, and whatever new columns you add, you need to make sure you are able to populate them with the right amount, the right default data. So there is a lot of operations that takes place when you modify a database, and you don't have that kind of time in today's time, considering the amount of data that is generated, because data is coming in. We yesterday we also mentioned that RDBMS data is representing like 10% of the data that is generated. Most of the data that is generated these days are images, then videos, right? Voice, And so we are no longer looking at kind of a web page content data, right? We are not looking at this kind of data. We are looking at images, videos, voices, and your social sites data. All this has to be processed very quickly. The amount of information that is generated and the amount of size that each of this data takes, these are not like, all of them are not very structured, right? They fall into the category mostly of semi-structured uh, or unstructured. Unstructured would mean something like like your binary data, right? Your images and videos and voice. These are all this you cannot organize them in a particular columns or something. That data is a part of one file, and that file you need to process it. It is in a very though the image is stored in a particular format or the video's voice are stored in a particular format, you still need to have a program to read that format and interpret that format and process that format. In a single video, you might have a video that is running for 3 hours, might have 10,000s and maybe a million images, right? There's so many frames that has been moving from nanosecond to nanosecond, and the quality of the image also makes differs the size, so to in order to so these days we are creating most of the applications are which are in demand are cognitive applications, right? So cognitive applications are all applications which is kind of, you can say, image processing, image, videos, voice, and all this kind of application is so important. If you just have a website and say I have a website is not enough. You need to these days we have smartphones everywhere, we have all kinds of devices everywhere, and people are not going to type on that small phone, or they're just going to say Alexa, please do something for me, please call my mom or something. So it is voice based commands that is coming up. So so we are looking at cognitive applications, right? And then we are also looking at IoT applications, right? Where there are sensors everywhere, and we are no longer, and the sensors are very small devices, right? A temperature sensor or whatever sensors, they are all in the car, all the devices are around us. So all this data is getting generated, and your normal RDBMS no longer suits. Your 90% of your data is coming in this format. So how do you manage that kind of size? And the second, so there is a problem. So the data, as I said, is coming, let's say, at 1 TB, or it may be in petabyte or zettabytes, right? Or exabytes. How the problem is, if so much data is coming, what is the storage space available? That is one of the problem statement. Your storage space has to will keep on the demand for storage will keep on increasing, right? The first day you might require 1 TB. The second, after some time that will become full. You need to keep on adding storages. So you add one more storage, and you keep on building the storage. This is called scaling, right? You keep on growing the storage space. So this storage is one of the problem statement, one of the problem with big data. How do you scale the storage? How do you grow the storage as the data is increasing? You need to store data somewhere, right? Before you process. The second problem in big data comes in your computations, right? How do you process so much amount of data? If there is a 1 TB of data, should you be processing 1 TB of data? The answer is usually you cannot process 1 TB of data. It's better to go for massively parallel processing systems, where so what is massively parallel processing systems is basically you're having many systems working together to solve one task. We spoke about task computing, right? So MPP systems are required. So you require multiple computers at the same time. So let me draw the computers maybe in a different color. So multiple computers with you require a lot of processors to manage your huge data. So not only the data has to be broken down into small split files or something, and small blocks of files, and then each block of file has to so there has to be some program which is going to work on that small amount of data. So the key to solve a big problem is by breaking down everything into small pieces, and making and managing small pieces over using multiple resources. So if you have 10 men to build a building versus 100 men or women to build a building, it will differ, right? Because 100 people can do the work much faster. So each person, if they do less work also, it's fine, but collectively they are doing a much bigger work, much faster work. So remember, whenever there is a big data problem, there is a problem of storage and there is a problem of computation. Now the third problem is your network, right? So so the question is why the color is not changing? Okay. The third thing that one is to keep in mind is your network. So it is quite possible the see, at any given day, not all the people are in the same place. Not every computer can do everything, right? So not one building will have all the resources. Sometimes the resources may be spread across, people may be spread across. So how are you so it is quite possible the system that you are having in one place, let's say in India, we are having a kind of a collection of computers, right? But somebody and you are trying to let's say you are in Africa, right? And you are having people over here. So let me, I don't know, my diagram is not good. Okay. Okay, so there's somebody in Africa over here, and that person is trying to visualize your data, right? So the thing is, if you're processing a data size of 1 terabyte, how much time will it take to transfer the data between India and Africa? 1 terabyte is a very huge data, so you cannot use your normal networks. You need to have a high speed network, and that's where the problem of this was the first problem which the scientists were facing. So that's when WAN was introduced, and WANs basically they were using high speed networks, and they were using leased lines or dedicated lines. So what are leased lines and dedicated line is usually when you subscribe for let's say you are subscribing to Airtel or Jio, right? That data is coming over some line, but that line is utilized by everybody in the community. So if there are 1,000 people subscribing to Airtel is not giving separate wire connection for each of them or separate data path for each of them. Everybody, the network pipe is the common pipe, right? And then it gets distributed to the 1,000 people or 10,000 people who are using that subscriber, the Airtel who are subscribing to Airtel company or Jio company. A leased line, a dedicated line means you are getting a separate line altogether, because you don't want to share. If you share, then you will there may be some that's why you have network problems, right? Sometimes you get network because somebody else is taking over your bandwidth, right? So the bandwidth is not shared in a leased line dedicated lines. And so also leased lines and dedicated lines are more like private lines, right? So they are created only for you, and we have this kind of leased lines, dedicated lines. Your internet is built on all these lines. Somebody has invested in these cables all over the world, and they are using this high speed networks. And the moment you have a high speed network, that only then something that is the size of 1 terabyte and processing over the internet to all over between continents or between two locations is possible. Without high speed network, it is not possible. And that is what the presentation initially was speaking about: high speed WANs, right? You require a high speed WAN network. And then the problem came, the 1 terabyte became suddenly, let's say, 1 petabyte. Now the sorry, should be 1 PB, right? This also should be PB and ZB. So now the not only it was the problem was no longer the network, but the problem was the data size. Now the data is too huge to manage. Now how do you manage? Can you transfer even 1 petabyte over the network? It doesn't make sense, right? So then what is the solution? The solution is one of the solution is creating a replica of the data nearer to the user, right? So you as and when data is getting generated over here, you replicate it over here in somewhere in Africa, and instead of the people in Africa going all the way to India, they will go to this local uh, your local your local infrastructure. So data grid is basically is first of all, when you're talking about grid, you're talking about a global solution, right? A global solution, or something which is spanning across a wide distance, right? So it can mean continents, it can mean countries, it can mean even cities. So you need to have a data grid kind of solution where every location has got some amount of data, and that data you're constantly replicating in different locations, which can be accessed by the local users. So that is what data grid is all about. But in a single location, what do we use? We use clusters, right? So a cluster is basically limited to a single location. And when we spoke about expanding the storage in one location, we are managing a cluster. Cluster is always bound to a single location, because in a single location also there is a problem of data data getting expanded all the time. So the problem is not only local, but the problem is also global. The task is not only local. You might right now we are thinking that there is only one task going on in between India and Africa, but yesterday we said that there can be many countries involved in solving a particular problem, right? So everybody has to be connected either locally or remotely. And sorry, hold on. So everybody has to be connected over high speed networks. That is what we said, right? AWS has its own global network, which is using their own lease lines, and since it is private lines, it is much faster. So if you are creating any service, you're creating a grid on AWS, you can use their internal network that will through which automatically you get those faster speeds. It will not go through all the public networks, and public networks are the bandwidth is shared. So but leased lines and private lines, the bandwidth is not shared, so it is much faster. And to solve data intensive computation problems, you ideally need those kind of high-speed networks. You require clusters. You require a data grid solution where your data is distributed into repositories. So every data has got some namespace, like we can say this is data about biological health information. So that can go in a health repository, and then you may have in health you might have different repositories. So it is like a folder structure that you create in your directories, right? And you kind of manage these repositories across different machines. So that is where your programs are, which are important. Some program has to be in place to manage and shift these files from place A to place B. We cannot do this manually, because manually it is going to take a lot of time and it is error prone. So it has to be automatic. So every time all that, as a business user or a business application or a scientific application or any application, we should never be worrying about how the storage will increase, or how the computation will be managed, or how we will replicate, or which countries have to be added. All those uh, uh, challenges are basically, about those problems, so you already design the system in such a way so that all those systems, all this uh, basic task is automated by itself. So then that is where we look at different kind of softwares. Okay, what software is there to create a grid, what softwares are there to manage a cluster, what programs are there, so that is like about the infrastructure. And the third part was the data itself, right? Somebody has to break down the data, and that is where that is altogether different tasks. So not only storage, computation, network, but somebody has to now do the work of breaking down the data, taking the data and shifting it to particular box, and telling program X to run its program on this particular data and give me the result. Somebody has to do that, right? So so the problem is not only infrastructure, so where we have storage, network, computation, but it is also data. So all these challenges go hand in hand. You cannot solve a data problem but not solve the storage problem. Your storage will get full, and then you will have no room for the data, and everything will crash. So that's so that is what they're speaking about data grids. And yesterday we spoke about metadata, right? Everything, especially when it is unstructured data, you cannot see what is there inside you cannot read it, right? You have to meta tag it. You can say, a particular image is, this is your, all the images of brain scans of so and so kind of patients. You meta tag it, and because we are dealing with lots of data which is spread all over, in your clusters and in your repositories across different locations. So you cannot work, if you want to know what data is where, then you cannot work on the data, you have to work on metadata. And that's why cataloging of data and metadata is important. You need to add in real time, as the data is getting generated, tag it, place it in the right place so that somebody can fetch it and use it for their computation. So here you hear about distributed applications, large scale high speed networks. These are all terms which I just mentioned. Distributed means nothing is on single location or single box. Distributed means the solution is based on multiple distributed computers, which can be in a LAN environment or in a WAN environment. So this is one example of a data grid, right? So here you see there is a storage facility in one place, and there is a information and discovery. So somewhere, if you want to know which information is where, that program is information and discovery. So your entire this entire grid is solving one problem, or maybe a particular domain problem. It is not solving many problems. No. So the problem statements are very big in big data kind of, or data intensive computation solutions. So you're looking at data grids. So this is how things evolved. First, they had to solve the problem of networks, and second, they had to solve the problem of infrastructures. So one of the things which one has to keep in mind is all this data grade is spread all over the world. So and there may be 10,000s or lakhs of people, let's say, involved in this system. And how do you manage? How do you secure this? So you need to make sure you have your network security policies. You use a each location will have its own administrator. If you've dealt with networks, you will always have an administrator, like you have an administrator on your computer. If you have another computer, there will be another administrative login. But if the two computers are connected to each other, am I going to keep on logging into different domains? No. So sometimes we see this example in your every day when we are visiting websites. They say login using your Facebook login or login using your Gmail login. It's single sign-on login, right? It is single sign-on login is kind of you can say a way of federating the logins and permissions, and which is spanning across multiple systems, which is spanning across different locations, different types of systems, etc. So these are some of the examples which we came across: a large hadron collider, bio. These were the earlier experiments that was done. Now the okay, hold on. Now, one of the problems of solving is if you're trying to solve, let's say, a problem, you're splitting the problem between India and Africa, then data has to travel over the networks. And if there is so much of data traveling over the network, that means you're spending more time in traveling than doing the actual work. So your traveling is a loss of you can optimize that time by working intelligently, by making the programs not by instead of having the program split across a wide network or wide distance. You replicate the program itself wherever it is necessary, where the data is. So so if let us in the same diagram. So let's say this storage is there, right, and this computation is there. Now all this computing, you can take this data and okay, hold on. So let's say some data is over here. You can take this data and put it on different computers. That is one part of the task, right? But other thing is you can also take the programs and place it over here on the same computer. It doesn't have to travel over the network. So you are taking the program and you're taking the data, both of them, and you're putting it in one place, and you're saying okay, please and at the same time, remember, we have broken down the data into smaller blocks, which means it is like 10 megabytes. So it is not like 1 GB. For 1 GB data would be broken down into 10 MB file or a 30 MB file, a small file and a program. So both of them, when they are in the same location, there is no need of traveling over the network all the time. And this is where Google came up with map reduce framework solution. So map basically this was trying to solve an analytical problem which doesn't use data grids exactly. This uses mostly clusters. You can still have grids, and you can still have different map reduce frameworks installed different locations, solving different kind of problems. But the idea of map reduce framework is to bring all together in a single cluster, in a single place, and replicate it, rather than having one program manage all the data spread across all the machines. You take that one program and copy it somewhere, in all the computers that requires a data, process it, and you come back with the result, and then you have a way to collect all the results and reduce the information or deduct the information as per the result that you want. So here they are giving you examples of some of the platforms like MapReduce is a Google platform. That was the first time MapReduce framework was introduced, and later so MapReduce. So we'll talk about that, and then Hadoop came, and then so these are not only there's not only MapReduce, but there's Hadoop. Hadoop is something which is open source. Everybody, the moment it is open source available to the public, everybody wants to use it. So Hadoop is there, Sector is there, Greenplum is there, Aster is there. Okay, so okay, hold on. Okay, so that's what we went through in this presentation, right? We went through an evolution of solving data intensive computing problems, and finally we came up with map reduce frameworks. So so the few things that we mentioned was it uses clusters, right? It is the moment you say clusters, it is in the same location. So why it is in the same location? Because to reduce latency. Latency is the time taken to travel, right? The network. The more the information is local, the latency will be lesser, right? Because you don't travel so much. If you travel more, it can take longer time to get back, because every time you travel, you send a request and you get a response. So let's see if hold on. Okay, can we take a 5 minutes break? It's 4:07 now. Can we start at 4:15 again? Okay, I need to just have some water or take a break, because we're moving into a different topic, right? Map reduce framework. Okay, so we'll just take 5 minutes break, and we'll start at 4:15 p.m. Yeah, don't log out or something. Just come back at 4:15 and we'll start. Yeah, thank you. Okay, so I am back. So time is 4:14. Okay, so can we start? Okay, so yeah, thank you for responding. So let's continue. Okay, so MapReduce, will continue with this framework. So we are trying to look at one particular way of solving the problems. Okay, it does not mean that everybody has to use MapReduce framework all the time, but it is one way of solving a big data problem. So the question is now how does MapReduce framework solve the big data problem? So yesterday we mentioned we take the big data, right, and this may come in the form of your input files or from different sources, wherever it comes from. You break it down into smaller block of files. Then you run the map function on this. So your map function is basically, this is a program that will work, that will process your single block file. Right, so that is what map function is doing. So if there are 5 blocks, so let's say this is a 1 megabyte 1 gigabyte file, and you divide this 1 gigabyte file into, let's say, 10 MB blocks, you will have how many files? You will have most likely 100 blocks, right? If you have 100 blocks, then you can create copies of map functions. You will have 100 map functions. Basically all these functions, they are doing the same thing. It's just that each map function is trying to uh, process one block at a time. So and each map function is trying to so there may be 100 map functions, right? And once data is once all this as and when this program finishes its processing, the output will can become, you can sort this data, or sort or shuffle, that is what the process is called. Basically you organize it, right? Once you have your results, you organize. Okay, we have got let's say you're trying to work on 4 buildings, and you send 100 people to work on 4 buildings. At the end, they are trying to report back to you. So when you're trying to, when this 100 people, they come back and report to you, you organize, right? You say, okay, building 1 group stand in one place, building 2 groups stand in one place, and please give me a report of building 1, building 2. That is what sorting and shuffling is all about. Basically after all the map functions, as in different map functions will be executing maybe at different times, right? It may, the result may be not all the results, we cannot wait for all the results, but as and when the results are coming in, the sorting and shuffling will keep on happening. And once it is sorted out and everything, then you, once you get the report, you deduce, okay, this is what the result is. So so you run the reduce functions. So reduce function is basically taking the result, the sorted result, you can say, from all map functions and coming up with the output, right? So this output can be output data, output result, output file. It can mean anything, right? Whatever the output is. Now just like there were 100 blocks and there were 100 just, I hope you all can hear me, right? Just like there were you broke down the data into 100 blocks, then you created 100 map functions, then you once all the map functions were similar, right? And each map function was doing the same thing, but they were operating on small block of file. So when you operate on small block of file or small block of data, you can finish your processing faster. And once it is done, you give it to the sorting and shuffling process, which will group, basically it will collate, separate say, groups of data in a proper slots. And once this is sorted out, the reduce function has to just process this sorted out data and come out with its own output. So the thing is, if there are 100 map functions, so can 100 map functions should be managed by one reduce function? No, there can be, you can create 10 reduce functions, right? So again, in this case, you are replicating the reduce functions also. Why? Because you want to save time. If you want to take the output of 100 map functions, you use 10 reduce functions to to process them in parallel, and then the 10 reduce functions will still reduce it further. The reduce functions will work together to create the output function, output result. So basically you collate all reduced data and output the result. Space. So this is how your map reduce process is working. It is a programming programming platform, right? It is a programming model, you can say. It has got nothing to do at a very high level. It has got nothing to do with the infrastructure, but it is more of a programming model. But the question is then, this 1 GB of data, somebody has to take it and place it somewhere, right? If you are looking at 1 GB, 1 terabyte of data, somebody has to manage all these files. And as and when your input and output files are generated, the program should know which file is where, and that is where the second part of MapReduce framework is your file systems. So the file system, basically it's a one set of program is taking care of your computation. The top part is taking care of your computation part. Okay, I will process the data as and when you give it to me. But another part is managing your data infrastructure, right? So that is done by the file system. So how does they do it? First of all, in any MapReduce framework, you need to define the cluster. So you can say I have I have 4 nodes, or let's say I've got 6 nodes, right? So on this node, each node, now all these 6 nodes you can create it as a separate process on your same computer, or you can have it, each node can be a separate computer. But at any given time, all of them have to be in the same location and connected using a network. They should be accessible with each other. Right. So what will be the duty of file system? The file system. So what will be the duty of file system? Will be to break down the data, right? Will be to break down the data and place it in place all the blocks. So it will say, okay, I will place 10 blocks over here. Another 10 blocks I will store over here. Another 10 blocks I will store over here. And then somebody like some other, the second part of the program is managing your jobs, right? So everything is a job, and everything, your jobs are divided into tasks. So this job, your job, as and when you're giving input files to the job, it will try to as I told you, the map function also has to be loaded, right? So it will say, okay, this file is here, so let me place my map function over here. Now the file is looking very dirty, but the idea is the map function is also getting over here, right? Wherever the data is, and we are getting into this particular step where the map function is now going to process the data. And then the job is also has to make sure the reduce function, where will the reduce function be? So the jobs make sure the reduce functions are, the diagram is not very neat, I'm so sorry. So the reduce functions are going to, is not necessary reduce functions are placed on the same computer, right? Reduce functions may be here, and maybe in the other part of the cluster. Now who is going to know which how many maps were created, where the reduce function is? It is the job tracker, right? The job tracker will ultimately make sure all the results are there is a constant shifting of results between the different computers as and when the processing is happening, because you're trying to solve one problem, but you've broken down the problem into between so many computers, or so across a different separate file system, that the data is scattered, the computation is scattered. Now we have to bring everything together, so somebody has to coordinate that part. So so there has to be a constant interaction between the job tracker and the File systems also, like job might ask the file system, okay, where have you placed all this data? Okay, where is the result? Where is the output? There's a constant once the reduce functions. So I hope you're not getting confused. So this line, it's a very small diagram. I should have created a bigger diagram. So these are reduce functions, okay. Then and these are map functions. Your map functions are also distributed. Your reduce function is also distributed, and this is your data lines. So there are three things happening, three kind of distributions happening in a single job. One, you're distributing the maps. Second, you're distributing the reduce functions. Third, you're distributing the data. So all the map functions are basically they operate on single block of data, and the reduce functions they take the results from the map functions, which is sorted out, and they come up with the result. Once all the data is collated and process, all the reduce functions are, they come out with an output. Somebody will then in the end, now I'm running out of colors also. Somebody in the end has to give the final result to the job, and that user who has initiated this job gets back the result over here. So the input files comes and as a job, then that job is divided into separate mapping and reduced task, and ultimately all of these things are coordinated to get together to come back with the result and give it back. So at a very high level, this is how MapReduce framework works. So here you see these are input data files coming from the left hand side. So this is your MapReduce infrastructure runtime. Your input data files are coming over here. These are basically your blocks of data, right? Your everything is kind of broken down into blocks of data, and each block of data is managed by a map task, which may be running on any particular node of the cluster. And in all these file systems, all the output that is generated, the runtime will pass it on to the reduce task, and the reduce task will create different sets of output files. Either it will be one output file or many output files. So here, they are explaining all the split files, right? This is file number 1, split 0, split 1, split 2, split 3, split 4. These are all splits and given to worker processes. Your worker process may be either doing a mapping function, or either it may be doing a reduce function. It may be doing either of this function, and who's controlling, who is interacting with all the worker nodes? The master nodes. You can have one master node, two master nodes. As we explained, that one master is a single point of failure, right? If one master, the machine goes down, then the master will never know what happened with all the worker nodes, right? So you may have multiple masters in the single cluster, and some worker nodes are writing to a file, and who is managing all these files is a file system. So here you see left hand side there's input files, map phase, then your intermediate files, reduce phase, and output files. So there was one, for this from the assignment perspective, I had mentioned that you need to go through this course, right? The big data course of Digital Vidya, and I shared you this link. So this is one of the chapters in this, which I felt was important. So here, it's saying that a map is taking a big data set and dividing into small data sets. It combines the output in the end, and here you get the output. So on every block of data, you do some work over here. So the same work is done on different sets of data. So here they are taking an example of, let's say you have got a lot of files. Okay, in this case they are giving you two input files. So there are two files with different words in each file, and what the program has to do is give me a count of each word. So there, how many times the apple is occurring, how many times the orange is occurring. So so how does this process work? So there is a input file. So there are two files which is converted into your your blocks, right? So this may be 1 GB file, or it may be a very big file. So you take this file itself and break it down into multiple files. So when you convert it into when you split it into different files, you get in one file apple, orange, mango is stored, the second file the other data is stored. So the data is split across all the files uniformly, which means every block will be of the same size. And so it will going to if you have every block of the same size, you can deduce how much time it is going to take to process each file. So every and then the mapping function, what it does, the mapping function, it says okay, in this file I will take each word and add a counter. So this mapping function, when it reads the first file, it finds out the apple is coming one time, orange is coming one time, mango is coming one time. So this is what the mapping function is doing. It is tokenizing means you are taking a string and taking each word out of that, you're taking an entire sentence or entire set of words and tokenizing it and breaking it down, filtering each word and giving some value to it. So it is creating a key value and a result of this. So if there were two apples in the first file, this would have been apple comma 2, where apple is your key. And what is the count? 2. Yeah, because apple is only coming one time in the first file, here you are saying apple comma 1, but it does not mean it will be 1 all the time. Your key, so there is, so mapping, they work in keys, right? So if you have a key, then okay, this key is having this value. It is like tagging, right? This data has got so much count, this data has got so much some other count. So whatever data you're working with, you always have to organize it in the format of key and value. Okay, so in this case they have decided that the name of the word itself becomes a key. So the first mapping function, it tried to come up with the result, and the first result was apple comma 1, orange comma 1, mango comma 1. The second mapping function, it read the second block of file, it came up with the result orange 1, grapes 1, lychee 1. And the same way, there were 4 mapping functions which were executing at the same time on different nodes, and they came up with their own result. And what happened after that, the sorting and shuffling program organized that information. Okay, apple 1 is coming from this particular node, and this mapping function has got this result, but there was another count of apple done by some other mapping function also. So all those data, so in the first file you could have had 2 apples, right? So this could have been apple comma 2. In the second file, or there were no apples, it could have been nothing. And in the third file it could have been apple comma 3. So this counter would have depended on the data that was counted by the particular mapping function. So this is what is called sorting and shuffling. Once this is sorted and shuffling, the reduce function, then we write the program in such a way that whatever output is coming from the mapping function, we just have to increment the counter. Means we have to just add the whatever data is there for each key, you simply add it. That is what the reduction function program will do. That is what you're going to write it. So so remember, mapping and reduce function is something that you have to write. You have to write the logic for it. So this logic, reduce logic, what it does, it takes the sum of all the keys, whatever key values are there, it takes and produces a sum. So you reduce function, what do we get? Apple comma 4, grapes comma 1, lychee 3. So this result you got. Now there are 5 results you got, but it is quite possible the output data itself is very huge. It may be 10 megabytes or 1 GB of data. So you had 1 petabyte of information coming in, and let's say you had 1 terabyte of output itself. So are you going to save all the output in one file? No, you will probably, your final output will be a combination of many output files, where each output file is having which is giving you the results of particular set of data. So apples and grapes may be saved in one file, lychee, mango, orange may be saved in another file. So the output file also may vary. So this is how the word count works. So today I'll show you an example of this same program. Okay. So as I said, MapReduce framework has two components, right? One is managing your file system. So in your Hadoop system, who is managing your file system is the HDFS. Okay, so Hadoop file system, and the second part of the program is somebody who's managing the job, that is your MapReduce layer. So that is what they're showing, the Hadoop. They're saying this is a name node, and so your name node is like your master nodes, okay, and your data node is like where all the nodes where the data is, and so this is a task tracker. Now a task tracker is managing multiple map functions. So it is quite possible that one node is having 10 blocks of data, and if you have 10 blocks of data, you'll have 10 map functions. So somebody has to manage that task, right? So multiple map functions or multiple tasks can be running on a single node, which is managed by the task tracker. So the task tracker is constantly communicating with the main job tracker on the main master node and giving back the information. It says, okay, I've done this task, I process this data, and take it back. So there's a constant communication between the master nodes and the worker nodes. The worker nodes will have task trackers, and it may be a data node, it will have a map function or a reduce function. So this is the same example where your block here, you can see a blocks of input files have been created, your map functions are getting executed, then the third part is shuffling and sorting, then the fourth part is reduction functions are getting executed, and finally you're getting the output, and the files are written over here, and maybe their files are replicated somewhere. So that is what it says, everything is organized as K1 V1, means like we said, apple comma 1, orange comma 2, right? So those are, your apple was your key, and the second part was a value part. So this whenever you're dealing with a map reduce kind of solution, it is based on key value pairs, and you operate on key value pairs. So this may be important for big data, but not important for for us in terms of cloud computing. But anyway, if you're doing a big data course, then this you should do this entire course, because it covers a lot of other aspects of MapReduce. Okay. So now that we have understood how MapReduce function works, we took an example of word count. Let's look at one example, right? So today I have kind of uploaded computing assignment file. I have uploaded, I've added one file in this, the installation guide. So this might be useful to you in case if you're doing the Hadoop assignment. So so if you access this particular, so download this installation guide and you can follow these steps if you want. So this install this particular link is it explains you how to install an Hadoop, and your Hadoop is dependent on Java. It works on Java, so you need to install Java also before you install Hadoop. So these are the commands to, there's some of the commands where you can install your Java over here. So and so if you run this command sudo apt install default dash ddk, it should install Java. And you need to install SSH, PDSH, and this last one. You need to run, first update the operating system Ubuntu, and then install SSH, then install PDSH, then install rsync, and that should be, others are optional. Okay, so let us see if we can, just wanted to, I have not shared you the, means I've shared you the website name. So you need to download that tar file first, okay? Before you cannot, it. So let's see, something is here, download. So there's a mirror site. So this Hadoop 3.30. So you see there is a tar file over here. It's 478 MB, and so this is like your zip file. This will contain your Hadoop. So I have this version of Hadoop over here. This takes a little time. So what I did was, once I I installed Ubuntu. First, as I told you, you need to install all that commands which I mentioned, right? Which was sudo apt-get update. So you need to run this command over here, like something like this, right? Apt-get update or something. So I'm not going to run it because it's going to take time. But in the end, definitely you need to install Java. Where is that file? So you can go with this command also if you want to install automatically. Sudo apt install default SDK, and install something like this, right? So this will once it installs Java, you need to set the path for Java, like where Java is installed. Now if I say Java dash dash version, okay, Java, yeah, so it says I have a OpenJDK version 1.8.0275. So you need to modify, if you want to add the path, you need to modify a file called source dot you know uh, basically dot profile file. So let me open a text editor. So it is in your home folder dot, where will I get it from you? It's not displaying that file. Why? So this text editor is basically, it doesn't go to that folder or doesn't let me, maybe I'm missing something, but let me just, you need to, so there is a file, so let's say I say cat, this is your root home folder, so this is same as home slash James on my box and dot profile file. So let's see what is there in this file. So if you see in this file, I have a I define Java home folder, right? I'm saying where is my Java home folder over here. So this line you need to add in dot profile file, and then you export the bin folder. You add the bin folder of Java home. So Java home is slash user lib jvm java 8 openjdk whatever slash bin. You're adding to the path. This is how you create a path. Path is equal to $path, which means the old path plus this path. So next time when you say Java dash version, it will easily come to know, okay, this is your Java home. So Hadoop has to know where Java is installed. So it tries to find out this, look at Java home, what is the setting for Java home. So that setting you need to put it in the dot profile file. And wherever you're installing Hadoop, you need to again create a setting for Hadoop home. And so in my case I've installed Hadoop in Hadoop 2.10.1, and I've also added the path. You need to add the path Hadoop home slash sbin, and you need to also create Hadoop class path, where you need to give the path for tools.jar. It is dependent on this file, so give that path also over here. So all these settings have to be done in dot profile file. And so every time, so what is that dot profile file? Basically it is a file that is going to be executed every time you start your machine, or you can manually start execute dot profile file by doing typing this command source and giving the path of the profile file. So this is going to run that commands which is there in dot profile file. So if I say echo dollar java underscore home, it says this is the setting, right? And if I say echo dollar Hadoop home, then I get the Hadoop path over here. So you can install Atom or some text editor where you can easily open that file and write it write it to that particular file. So what I did was I created a Hadoop folder. So if you notice over here, and whatever tar file you get, you need to run something, a command such as zxf and the name of the file, tar file, whatever, my tar file dot tar dot gs. So once you unzip this file, a folder will be created in this. In my case it was hadoop dash 2 point. So all the tar file was extracted in 2.10.1. Oh yeah, so you see the entire bin and everything was stored over here. Once these files were created, I created a Hadoop home entry in the dot profile file. I added the part to that. So that's what it says, modify dot profile file. And you can test these are some test commands you can test over here. Then it says you need to edit two XML files. Basically, you need to configure your your Hadoop. So there is a file called hdfs-site.xml that you need to have these entries over there, and then you need to modify core site.xml, and you need to have these entries over there. Then you need to run all these commands. So let's say SSH. I've done all this, but at the end okay, this is taking time. Okay, let's try to, what's the time? It's going to take time, okay, if I want to show this demo. So first, you remember we have installed SSH on the top, so this command you need to run, and then you need to generate all these keys as given over here. So let me clear. So SSH localhost, something like this. You need to run the command. Provide your password, admin password, and this will do whatever is necessary. After that, you have to create the file system. So you can create a file system by running this command. So what is the command? Bin hdfs name for dash name node dash format. Now remember, name node is your master node, and so you're creating a hdfs file system which is going to manage your files. Okay, oh, I'm not in the right folder. Now in this, the bin folder is there. If you notice over here, this is your bin folder. So I'll run this command now again. Bin slash hdfs name node dash format. So this is like formatting your hard disk, right? So, but in this case, the hdfs file system is inside your Ubuntu. It is not exposed. It is created within Hadoop. So your file system has been created. What is the next step? Then it says start the file system. So you can start the file system by why is not copying? Okay, what was the command? sbin slash star dash dfs dot sh. So sbin slash start dfs dot sh. Okay, so it is trying to start name nodes. You can see it is saying I'm starting the name nodes as per the configuration in the file. So I'll give the password. Okay, and after this, okay, it's again asking the password. It is trying to start the data node. Okay, it was trying to asking the password because it's want to start the data node. So now, so I hope you all understand the difference between name node and data node. So there is a second data node that is created. So there is one name node and two data nodes. Right, so everything has been so it has already started, and the nodes are created. The file system was formatted earlier. Now we will see http localhost 50070. Okay, so let us go there. So it's computer slow because of Ubuntu and OBS Studio is running, no, that's why. So this is connecting to your Hadoop system, whatever is running on your box, and it is giving you. So let's click overview, and you can see something, or you can get all the data over here. So it says there's a live node, which is one live node is there. And you can look at the data nodes. It says there is one data node, so probably is giving you the count of primary nodes. Okay, so your Hadoop is running, and through this link you are able to connect to the Hadoop system and see what all is running. Now next step. So now you need to create all these folders inside your file system. So because so this is going to take time, I guess. First clear. Start copying. Bin slash sdfs dfs slash dash make directory slash user. Bin slash sdfs dfs command is make directory. So now this command make directory is running in the inside the Hadoop file system, okay, not on your virtual box. So this is in SDFS is a file system inside your VirtualBox system, which has its own file system. So here we want to create a folder called slash user. Okay, so the folder is created. Then you want to create a Hadoop folder inside your user folder, and then create word count folder inside your Hadoop, and then create input folder inside your word count and output folder. So okay, so we need to create all these folders before we test, for testing purpose. So user, so in this I need to create Hadoop, right? Hadoop folder, right? Right. Inside Hadoop folder, I need to create word count folder. This is for my application. Inside word count, I want to create an input folder where I will place all my input data files. Inside word count, I also want to create output folder where I will place all my output data files. Okay. So then I want to will this copy. So I want to copy from my virtual box this particular folder all the input data files. It is already placed over here, so I'm going to just copy it and put it in the Hadoop file system in the input folder. So this is your it says copy from local, and this is your local VirtualBox folder, and this is your the second parameter is your directory path of your Hadoop folder. So let's go back. Let's clear this. It's not copying. I have to keep typing the commands. Okay, bin slash Hadoop fs dash copy from local whatever dot dot slash tutorial file 0 dot star into this folder slash user Hadoop word count input bin slash Hadoop fs. So it is bin slash Hadoop is it dash fs? No, it is fs dash copy from local. So fs dash copy from local. So what is your local folder name where you're on your VirtualBox? It is in dot dot slash tutorial 101 slash file 0 dot star. File 0 star means all files with that starts with file 0. Okay, so so I'm copying from that dot slash tutorial 101 folder all files starting with file 0 star. Where I want to copy? I want to copy in Hadoop system where slash user slash Hadoop, this folder I just created, right, word count, and place all the input files in this input folder. It says what? No such file. Tutorial 101 is there, no? Oh, the input files are not here. So where are the input files? Okay, I have placed all input files inside this folder. Okay. Hold on. Somebody else. I heard something. Right, so okay, anyway, the file is in input folder over here. So you notice there is file 01, file 02 over here. I want to copy this in that input folder. If I see what is the content of this, cat 01 has hello world by world. Okay, what does second file as? Second file as hello Hadoop goodbye Hadoop. Okay, so there are so I need to count the number of words in this file. So let me go back to where I was here, right, and then here I ran that command. Let me clear the screen first. Oh, I have to type the command again. Bin Hadoop fs copy from local. This should be slash input file 0. Bin Hadoop fs copy from local. Okay, the folder was input, right? Input folder slash file 0 star. Where I want to copy? User Hadoop. Okay, word count. Inside this input folder I created. Here I want to copy. What is it? No such file. Okay, so this time the command has worked. So your files are copied, and so now I can run my program. Right, so what does this command does? It takes your compiled word count. So if you notice, I've compiled jar cf over here already. This commands I did not run it for you, but you need to run these two commands to compile your word count.java file and create a class file. So once you have that, you can run your Java program over here. So here I'm running word count, and it is reading the input file from this folder input, and it is outputting the folder to output folder. So this is not going to copy, is it? Okay, the command user slash Hadoop slash word count slash output. So now my program Hadoop program is running, my map reduce functions are running, and it has creating all the output over here. So this is our word count. So if you notice, everything is running and it is finally over. So now if I see my output file, how do I see the output file? I can read what this all my output file will be in this folder, right? Output folder, and it would have created this part 0 file. So let me run this command. Sometimes characters are not getting typed properly. What happened? No such file. Oh, it created the folder name I specified wrong over here when I ran the program. Let me user Hadoop word count output, no? Okay. So I'll run the program again. That folder name was wrong, right? That's why. Where did I create that file? HADDOP. Let me see if I can find those files over here. HADDOP. It will not find. Yeah, it says that's correct. Everything seems like I'll have to rerun. To check the folders, right? ls command. So my files are here, and what about the output folder? Okay. Is bin. Let me stop the file system once, and let's see. Stop dfs.sh, right? Where it is? Stop dfs.sh. Okay. So it is asking the password before we stop the nodes. So I am also using Hadoop for the first time, so some errors are new to me, and that's why it takes time. Okay, so let me start the file system again. Okay, then let me run that program. What's that says exception in thread file already exists exception output folder. So let me, don't know what's happening, but let me see if I can remove that folder first. This is right. How do we, it's not removing. Okay, let me create a separate output folder. Okay, so how do I create a separate folder? I'll create another directory. Make dir slash user Hadoop output 2. Okay, let's try this. Please work. Right, now let me run my Java program. Instead of putting the output file in that folder, I'll put it in some other files. Okay, was it the same error? Some silly mistake I'm doing. I don't know what exactly is the problem, but you should get your all your output data, and the results will be that there in that file. Input path does not exist. Okay, so let me create the input folder also. Make dir slash input 2. Okay, right, then I'll copy the files. Okay, this is the one, right? I want to copy from this to input 2. Right, then I want to run my Java program between input 2 and there was a slash here, so let me put a slash. Hope it works. Session ID some. SSH localhost. Yeah, I don't know what is the problem. I'll have to rerun all the commands. So I think it's a lot of time is gone. So basically, I would have repeated all these entire steps again to recreate the entire process. So once maybe I should just do it. Okay, let's try. Let's redo everything. It's tiring. Okay. Okay, clear. First, let's format. Just because of that one spelling mistake, everything. Right. So this is formatted. Right. So this time we will just create simple folders. Uh, this time we will not create complicated folders. We'll just create one input folder and one output folder. This dash is a problem. And let us create an output folder. Right. And then what is the next command? I want to copy all the files, right? And this was not tutorial, this was input folder. It's over here. And where do I want to place it? I want to place it in input folder. So this dash was a problem, is it? Again, same thing. Okay, so it has been So all the files have been copied over there, and bin Hadoop. So now this won't be there, it will be simply be input, and this should be output, right? And some silly mistake I'm doing, I do not know what. Okay, yeah, so we'll stop here for now, because there's some small silly problem which I am not able to detect as of now. But if you look at the program, let's at least look at the program. Okay, where is word count? This one, no? So this is your word count Java program, and if you notice, you need to implement extend mapper class in Java. This is the class which is used by MapReduce Hadoop framework. Once you try to implement mapper, it will force you to implement a map function, which is taking a string and breaking it down into key value pairs over here. That is what this function is doing, this map function. And there is another class that you're creating, is your reducer class, right? If you implement reducer class, then you have to implement reduce function. And in reduce function, what happens? You are taking the sum of all values, key, you're getting key as input and values, right? So whatever values you're getting, you're adding it over here. So in the end, whatever this output is been returned to the output file. So that is how this program works. You have to initialize all the mapper class, reducer class over here, and the output folder, input folder, and everything works automatically. So unfortunately, I was not able to show you the output because of some silly problem, but I have seen the output before. You run all the steps right from top to bottom, and whatever steps I've given in the PDF file, and it should work. Okay, if you are facing problem, let me know. So sorry, today's lecture was okay. Any other question anybody has? Okay, so yeah, so with that we finish our unit 3, and we will see you on the demo date. So thank you everyone. Have a good evening. Bye.